Welcome to Ask and Learn.
Hi all, Alex B here with another question on electrical resistance from Chapter 25 of Giancali's Physics for Scientists and Engineers. So this one asks us to evaluate the resistance of a hollow cylindrical wire, which is going to have an internal hollow section of radius R1, and going to have some sort of an external radius. Doing my best to draw a good circle here, of R2. And we're going to try and figure out what the resistance is to a current that is flowing from the interior wall to the exterior wall. So it's going to flow along this direction. And the way we're going to do that is we're going to look at a little differential element, which is somewhere inside. It's going to be at some radius, r. Let me use little r here. Usually we want to use lowercase letters when we're doing differential elements, and we're also going to use big R for resistance. And it's going to be changing by dr. Now we know that in general, our resistance is going to go like rho times some sort of a distance, d, over some sort of an area, a. So when we're looking at our sort of change in resistance, dr over this little change in radius, d little r, we should keep the same rho. Our distance is now just going to be dr. And our area is going to be the area of a cylinder now, which is going to be 2 pi times L, which is sort of the suppressed length dimension, which I haven't shown here, times R itself, because that's going to determine how large this circle is. So when we try and calculate our total resistance, that's just going to be an integral over this d capital R. Now rho and 2 pi L are all constants. So we're going to pull them out, and we're just going to integrate from R1 to R2 d little r over little r itself. And if we plug that in, we should find that our resistance is given by rho over 2 pi L times the log of R2 over R1, which is what the question asked. Now that was just part A. Moving on to part B here. Part B asks us to evaluate this for a wire who has a resistivity rho of 15 times 10 to the minus 5 ohms times meters, a length L of 2.4 centimeters, which I'm going to write here in meters, 0.024 meters, an internal radius R1 of 1.0 millimeters, and an outside radius R2 of 1.8 millimeters. Plugging that in, we should find that R is equal to rho over 2 pi L times ln R2 over R1, and plugging all these numbers, we should find that that gives us a resistance of 5.8 times 10 to the minus 4 ohms, or in more conventional units, we could call that 580 microohms. So obviously this is a very small resistance, and we expect a lot of current to flow in this direction. Now the last part of this question, part C, is going to ask us, okay, that was for, current flowing from the inside to the outside of the wire, but what if I want the more obvious direction, and I want to ask what is the resistance of current as it's flowing along the wire? Well, to do that, we just go back to our formula. R is equal to rho times L over A. And now all we need to do is calculate the cross-sectional area of this, which should easily be given to us by pi r2 squared minus pi r1 squared. So this is the total area inside of this sort of outside radius, and then we're subtracting off this little piece in the middle that's missing. Plugging in all of this, we should find R is equal to rho times L, that same 2.4 centimeters they gave us before, times pi r2 squared minus r1 squared. Here again, we're going to use the same values given to us before. Rho is equal to 15 times 10 to the minus 5 ohms times meters. L is going to be 0.024 meters. And I'm going to write R2 and R1 now in terms of meters because they're not going to cancel in the units. We need to make sure we keep them in meters this time. So R2 is going to be equal to 1.8 times 10 to the minus 3 meters, while R1 is equal to 1.0 times 10 to the minus 3 meters. And if you plug all of this in, you should find that our resistance R is going to be 0.51 ohms. More like what you'd expect of a typical wire. Thanks for listening.